This part will summarize all the manual calculation we took before. We will design a grid-connected PV system using a simple equations just to understand the concept of the, let's say, system design. So I divided in 5 steps. The first one is load demands, which is to get the required AC energy, and then defining the system losses, array sizing, configuration of the array, and the array layout or module arrangement. If we come to the first one, load demand. Here we need to know 3 important things. The first one is the number of equipment, the wattage for each device, and the working hours for each equipment. This is for the purpose to get the required AC energy. The second step, as I said, is to get the system losses. We know that for each part of the system there is a specific efficiency. There is efficiency for solar panel, there is efficiency for cabling, and there is efficiency for the inverter or the conversion. So to get the overall system efficiency, we need to multiply the efficiency for modules, efficiency for cables, and efficiency of the inverter. All of this actually to go back from the AC load demand to the DC required DC energy. For array sizing, we will get the size of watt peak using this equation. We know the DC energy in watt hour. We will divide it by the sun hours for that specific location. There is sun hour or equivalent sun hours for each location. You need to know this from, let's say, the ready-made solar maps. The second important thing is to know the number of modules of your array. And we can know this by dividing the array size in watt peak over the module wattage. By this, we should actually selected the type of our module, and we should know their specifications. And here is a snapshot for a module, and there is a specific information, and there are more detailed information in each datasheet. For array configuration, we would know the inverter size, and here is the, let's say, the equation we are going to use. There is a sizing factor, just to oversize or undersize our array. It depends on the location. We know already the array watt peak. We will multiply it by that factor, and then we will get the required inverter size. Another important thing is the number of strings and modules in series, and we already calculated this in one of the lectures, so we are going to use the same equations we used it there. And finally, the overcurrent protection devices, we will calculate it by using this equation, 156% of the module short current circuit or short circuit current. We come to the final part, which is the module arrangement. In the module arrangement, we need to consider the inter-row shading or the shading created by any, let's say, objects in the area that is going to be used for installing the PV modules. So there are some equations we are going to use it, and also if we have a certain area, we want to know how many rows that we can put it in that area, how many columns of solar PV panel we can install in that specific area. So I made one Excel sheet, and in that Excel sheet I put all the equations, I linked it together, and I'm going to share it with you so that you can practice in your home, and I'll put assignment at the end of this lecture so that you could design your specific system and send the result for me just to share some information. So I will start from now in that Excel sheet, and I put all the equations for each step, and as I said, you could do it in your home and for your own system and share it with us. So for the first step, the load demand or AC load demand, I said that we need three important information. We need to know what is your loads like lights, TV, air conditioner. We need to know the quantity for each equipment, the wattage for each equipment, and the working hours. And this sheet will calculate the, let's say, the wattage for let's say the wattage for all equipment, and also the energy and the total AC energy in watt hours by using this simple equation. Numbers, the energy in watt hours is equal to the number of equipment, the power rating, and the working hours. So this is for the load or AC load demand. For system losses, as I said, we have some efficiency for the cable and efficiency for the inverters. So we consider that the efficiency for the cable as 98% and the inverter is 96%, so that we get the efficiency as 94.8. And the energy, to get the energy, we say that we have the AC energy in watt hour over the efficiency we calculated. We get it as 106,909 watt hour. And this is the bar chart which shows that if we get the, let's say, the output DC energy, we will lose some energy in the cabling, and we will use some energy in the inverter, and then the AC energy will be the, let's say, our final energy yield. Now for array sizing, as I told you that we need to know the equivalent sun hours in your location. For example, in Riyadh, the equivalent sun hours is 6.3 let's say hours a day, so that we can size the array as the array size in watt peak is equal to the DC energy in watt hour we got it from the previous slide over the equivalent sun hours. We get the, let's say, the required DC energy or the array size in watt peak, or we could convert it in kilowatt peak for let's say easy reading of the numbers. We come actually to some specific information from the selected type of PV panel. I selected a PV panel which has a 320 watt peak, and it has this open circuit voltage, short circuit current, and these are the, let's say, this is the temperature coefficient for the rating. We are going to use it in next step. So by knowing the array size and also the module watt peak, we could calculate the number of modules you needed in your system. So we just simply divide this number, the watt peak, the array size in watt peak, over the rating of the solar panel. We get 54. Now we come to array arrangement. An array arrangement, actually, what we are going to do is that we know now the system size and watt peak, and we know the number of modules we needed in our array on our system. So we need to calculate the inverter size. So in inverter size, actually there are a big, let's say, debate about the inverter size. You will see that in some places you need to derate your or undersize your inverter, and some places you need to oversize it. So in our case, we oversized our inverter to 1.2, so that we had an inverter with this size actually, and we should, let's say, select the available standard or the available let's say size in the market. So the next available size in the market was 22,500 watt peak from SMA. So this is the selected inverter size, and these are the parameters for that let's say inverter. We got it from the data sheet for that inverter, like the maximum input voltage, the minimum input DC voltage, the MPPT range and number of MPPT, and the maximum input DC current. We are going to use all of these parameters in our calculation. So you remember in one of the actually that we need to correct for the temperature, for high temperature and for low temperature. So we need actually to calculate let's say the temperature coefficient for open circuit and temperature coefficient for maximum power, and we can calculate this actually from, let's say, the panels or solar panel specification. And here is the minimum temperature, which is minus 10 degrees Celsius, and here the maximum ambient temperature, which is 60 degree, and we have the knock temperature, we consider it as 40. Note that we said that the maximum ambient temperature, which is different than the cell temperature. So if we want to know the cell temperature, we need to use this equation. We will substitute the value of ambient temperature here. G, we will consider it as 1000. Knocked, we have it as 40, and then we will calculate it and we get it 85 degrees Celsius. So from that, we will use this equation as we used it in our, let's say, previous examples, and we will get the minimum temperature, open circuit temperature, or and also the maximum, let's say, the voltage at maximum temperature. So these are our limits. These are the minimum and maximum voltage of our cells, the corrected ones. From these, we could actually calculate the maximum number and minimum number of modules that can be connected in series. So based on these actually equations, we found that the minimum number of modules is 4 modules, which can be connected in series, and the maximum is 14. So we need to select, let's say, the number of series connected module between 4 to 14. So in our case, we selected as 9. If you just notice with me that if I selected a different number, like between 4 and 14, like 8, for example, we will get like unreal, let's say, with some decimal numbers, number of strings. We want it to be like an exact number, or we can divide them into, let's say, into types of strings, or two types of numbers in strings. And for example, now if I selected 9, I will get 6 number of strings, and each string I will have 9 modules connected in series. Alternatively, you could, as I said, for example, if you prefer to use, for example, 8 in each string, you wouldn't get a real number. So that you could, for example, said, I will have 3 strings with 8 modules in series, and we will have like 4 strings or 8 strings, for example, with 5 modules connected in series. For example, you could do it that way. But what I did, actually, I could find a number between 4 to 14, which give me a real number for the string. So I selected 9. It will give me 6 number of strings. And this is the equation we used it as to calculate this number of strings. So this part we use it to verify our selection for the number of module and number of strings. So you see that if I change it, for example, to 5 modules in series in each string, I will get some values like this, out of range 220, which is less than the let's say operation range for the MPPT. So it's better actually to increase it so that you will be in the range of MPPT. So I will change it to 9 so that I'll be in the safe side. And also let's say the inverter input current, I have some limitation on this. So if we see that the maximum input DC current is 63 ampere, and here we calculated as 37.44, and still we are in the limit, so it's okay for that for us. Now we are going to calculate the overcurrent protection devices using this simple equation. 156% multiplied by the module short circuit current, we get 9.73. Why we need to calculate this? Because in our system we will need a combiner box. Why? because our MPPT tracker, we have 2 MPPT tracker in our inverter. So, and we have 5 number or 6 number of strings. We will combine each 3 strings in one MPPT. So we need some overcurrent protection devices, and we need a combiner box to, let's say, combine each 3 strings in parallel, and we will get and we will connect it to one of the MPPT tracker. Here we come to the final part, which is the panel arrangement or array alignment. We need to know the length and width of the solar modules, and we get it from the data sheet. Also, we need to know the location altitude, the altitude of the place you want to install the system, and in our case it was 43.38. From these information, actually we can calculate the let's say the distances in order to avoid the shading or inter-row shading from one row to the other row. So in order to be able to calculate this, we need to know the angles, and we need to know some dimensions. For example, like H here. We already know the tilt angle for this place, which is equal to the location latitude, which is 43.38. This is for beta. But for gamma, which is the shadow angle, still we don't know it. And also we don't know the distance from the beginning of this module or from this row to the other row. So we need to divide them like D1 for the first, let's say for the let's say this module or row, and D2 from the end of this row to the beginning of the other row, so that we can actually find the total distance from the beginning of this row to the beginning of the next row. So H we calculated by using simple equation. We already know the width of the panel, and we will multiply that the let's say W multiplied by the sine beta. We can get the, let's say, the height. And also D1 we can get it by the same equation, but we are going to use cosine the latitude. Now we know D1 and H. To know the shadow angle, there are 2 ways. Either to use this simple equation, 90 minus the latitude minus the earth axis tilt, which is 23.5, or we can get it from the let's say the charts that is available in weather let's say website. For example, I got this from one of the weather websites, and it's given me like 42 the altitude for the sun, and the 21st of December at noon it is 42, which is very near to what we calculated, which is 42.12. So if we want to get it from any of the weather website, actually we need to go to the 21st of December of each year. At noon we select the altitude or the sun elevation angle. So from this we can calculate D2 by now we know this angle, and also we know H. We can calculate D2 and then find the total distance from the beginning of this row to the beginning of the other row. And this is what we did actually here. So by this, now we actually know the distance from the beginning of this row to the other row, so that we can avoid shading from one row to the other. There is one last, let's say, task, which is actually knowing how many rows you could have in your area or the available area you want to install the system in it. So we put the length and width of the available area. For example, I put it here 25 and 10 meters, and we found that we can install up to 7 rows and 16 number of columns in this area. With the total, we can install total 112 number of modules, where in fact in our system we need only 54, which is more than enough, which means that this space is more than what we need to install the system. Actually, you could reduce it if, for example, you could say maybe 15 to 10 is enough. Yeah, it's enough. 13. So 13 by 10 is enough to install it for our system. But there is one important information, is that whenever you are going to let's say plan your your panel or array layout, you need to consider some spaces for maintenance and for cleaning. For example, near to the parapet, for example, here near to the array, in case of it is a roof mounted, or spaces between the columns for easy of maintenance and cleaning. This is all actually what we wanted to share with you in this example. I hope everything is clear. And as I said, I'll put an assignment, and in that assignment, I'm going to share with you this Excel sheet so that you can calculate your own system and submit it at the end as a homework. Thank you very much, and I hope you benefit from this, let's say, example or exercise. Thank you very much.